Hi, today we will start to solve the problems in mechanics by a different way of solving them. Because so far we were using the Newton's laws, namely, very shortly, F equals ma type of equations. So, net force on an object is equal to mass of that object times the acceleration arising because of that force applied, was the Newton's second law, obviously. And it was a very simple case. It was easy to apply to the relatively simpler cases. However, there are some cases where this equation is not powerful enough to solve them, because the forces may change during the time. It may be quite difficult to follow the forces, how they change, especially when there are more than one force on an object, and those forces are changing, or in a very short time interval, so that we are not very sure about the way forces change, for example. In those cases, we need a different way, and that different way is indeed a very powerful one, relatively simpler, relatively shorter, and it comes from Joseph Louis Lagrange. So Lagrange between 1736 and 1813, so it dates back to the 18th century. So what is that method and what is the equation? Because Lagrange's equation, of course, it's also called Euler-Lagrange equation, because there's a period of roughly 3 decades between Euler and Lagrange. Euler is roughly 30 years older than Joseph Louis Lagrange. But they are basically called Lagrange's equation. It's a simple equation. Let me first give the equation and then try to see how we derive it in a mathematical way and apply it to some cases where it is more difficult. It is maybe not difficult just to check the validity of this equation that I will give you, but also it is quite applicable for cases where this simple law is not very applicable. So let's first define a quantity called Lagrangian. Let us define a quantity called the Lagrangian. It is generally written by capital L. And not to confuse with angular momentum, maybe in some cases it is written with a curly L, etc. But what is the definition? Because in this analysis, instead of forces, we will be dealing with energies, potential and kinetic energies. So, energies and their derivatives will play a big, important role in this analysis. And the Lagrangian is defined as the difference of the kinetic energy of the object and its potential energy. Not the sum, but the difference. Let us define a quantity called the Lagrangian L. L is defined as T minus V, where T is the kinetic energy, V is the potential energy. Where T is the kinetic energy and V is the potential energy. But be careful, it is a subtraction, not an addition. Because, for instance, the Hamiltonian is the sum of kinetic and potential terms. Of course, Hamiltonian comes into play in quantum mechanics as well. But in classical mechanics, Lagrangian is a very powerful quantity. It is the difference of the kinetic and potential energies of an object. Of course, there may be more than one type of potential, as we will see in the example. But let's write the equation first. Lagrange's equation is the following. We have a derivative, d by dt, time derivative of del L by del, let's say, x dot, for instance. If x is the variable, if the object is moving along the x-axis, or if it is moving along the y-axis, it may be y dot. Or maybe the angle is important, it is changing as we will see, so it will be theta dot. So d by dt, del L by L is this Lagrangian, del L by del x dot minus del L by del x is just 0. So this is the equation called Lagrange's equation, and it will be quite helpful, powerful in several applications. Let's apply it to a very simple case, for instance, to check. Of course, I will try to derive this equation using some mathematical tricks, but let me just apply and check the validity. For example, if something is thrown into the air, of course we can solve it by kinematical means. Let us check the equation, the validity of the equation, by a simple example of throwing something, a ball, into the air, for example. Let us check the equation by an example where we throw a ball into the air. So here is the ground, y equals 0. Here is the ground, y equals 0. If the ball is initially here and it is thrown into the air, let's say vertically up, it goes up and turns back, etc. Normally, of course, we say that if you didn't know about this equation, we would use Newtonian mechanics, and we would say that, for example, this is the related axis is the y-axis if you use y, or you can use z if you consider the surface as xy plane, but the vertical axis may be z. Let's say y or z, let's use y-axis as the vertical axis. Then of course y double dot will be, for example, minus g, which means the acceleration of the object, or you would write my double dot is equal to minus mg, for instance. After you cancel the masses, you will obtain y double dot equals minus g, which is the acceleration of the object, gravitational acceleration, and it is pointing down when it is falling, whether upward or downward doesn't matter. During the flight, its acceleration is downward and the magnitude is minus g. So we should obtain this result at least by applying the new equation to the energies, difference of the energies. So for such a system, what is the kinetic energy first of all? The kinetic energy is, let's say, if it is thrown vertically up, it is 1/2 m times Vy squared. We would write in physics 101, but now we don't write Vy. What do we write? Instead of Vy squared, we will write y dot squared, because y dot is the velocity along the y-axis. So the kinetic energy will be 1/2 m y dot squared. What about the potential energy is, the potential energy at a certain height from the ground, from the level of this throw, it will be m times g times y. Gravitational potential energy. And assuming that those heights are not comparable with the radius of the Earth, so we don't use the gravitational potential that we learned last time as minus g mm m1 m2 or R type of potential, but instead the simple gravitational potential energy that we are using in Physics 101, mgy. So let's use these energies. What about the Lagrangian L? Then L will be T minus V. So L will be T 1/2 m y dot squared minus the potential energy mgy. So this is the Lagrangian that we have to consider here in these two terms. But of course we don't have an x dependence now, we instead have y dependence. So this has to be written as not x dot but y dot, and this not x but y, because we don't have any x dependence in the motion. Alright, now let's find the required derivatives. Del L by del y, for instance. First one, let's use this one. Del L by del y. Del L by del y. And as you see, there's no y term in the first one. We only have here minus mg. We also should have del L by del y dot. Del L by del y dot. There's only one term having y dot, which is the first. There is no y dot here. So this becomes 2's cancel and y dot. And y dot. But we should apply this time derivative d by dt to the first term. Therefore, d by dt applied on del L by del y dot is d by dt on this term m y dot. It will be, since m does not change, m doesn't have a time derivative, it is the second term which will be differentiated, and y double. So let's now apply and put them in the given equation. First term is this one, m y double dot minus the second one, but this is also minus, plus mg is equal to 0. So as you see, we obtain this expected equation. If you cancel the masses, y double dot is simply minus g as expected. So it is working for this simplest possibility of throwing a ball in a vertical sense. Let's apply it now to the case of a mass spring system. Now, let us apply it to a mass spring system. But on a horizontal level. So for instance, we have a spring and it is, let's say, stretched. But on the other hand, it has some velocity. But this is the amount of elongation x. But on the other hand, it has a speed. Assuming it has a certain velocity, it is moving maybe to the right, maybe to the left, but the magnitude is x dot. We don't use v as the velocity, we use x dot or y dot. And we don't use acceleration, it is x double dot, y double dot. Alright, now it has a mass m. Assume it has a mass m. In this case, what is the kinetic energy of this particle object? It is 1/2 m velocity squared. We don't write velocity v, we write it x dot. So we write it x dot squared. And the potential is simply, remember, 1/2 kx squared. Therefore, Lagrangian L will be t minus v, which is the difference of these two terms. 1/2 m x dot squared minus 1/2 kx squared. At this stage, we have to apply the equation and take the necessary derivatives. So del L, but this time we have x dependent, so del L by del x. The necessary derivatives are del L by del x. It is just, since it has only the second term having an x dependence, it will be negative 2's cancel kx. And del L by del x dot. Only the first one has an x dot dependence. 2's again cancel. It is m x dot. If you apply the time derivative once again, now the time dependence, time derivative d by dt on del L by del x dot will be d by dt on mx dot, and it will be, as expected, mx double dot. So now substitute these terms in the equation. Of course, now we don't have y, but we have x dot, and x. So the first one will be mx double dot. Substituting them in Lagrange's equation. First term is mx double dot minus the other term, but it is already minus, so we have plus kx is equal to 0. And as you see, this is the equation of the equation of motion for a particle of mass m attached to the end of a spring of force constant k and making oscillations back and forth in a frictionless medium according to some sinusoidal function. We know the solution, so this is nothing new right now. It doesn't give, or it didn't give so far, an extra ease for solving problems, but it is just for checking the validity of the equation for two cases. Let me say it is x double dot plus k over m, x equals 0, and the solutions we know x of t are a cosine omega 0 t plus delta, and we have already seen and applied, did some applications on this these oscillating systems previously. All right. So what is new for this equation? It will be applied to some other cases where it is quite difficult to get the solution by some equations based on Newton's laws, for instance. Let us apply it to a new case. Let us apply it to a new case where, let me write it as an example. First of all, this is also a mass spring system, but it's like a pendulum, spring pendulum. So this is a spring of force constant K, and a mass M is attached to the end of it. Its normal length is B, its unstretched equilibrium length is B, and it is, let me write it here, a bob of mass M is attached to the free end of a spring of equilibrium length B, spring having the equilibrium length B and force constant K. A ball of mass M is attached to the free end of a spring having the equilibrium length B and force constant K. Assume that this spring is made to move along a line because of this light rod. There's a very light rod here, very light, massless rod, so that the spring does not bend and moves as a line. All right. Write the equations. Write the equations of motion for this mass spring pendulum. Because what happens, as you see, for example, if you have a spring and a ball like this one, so this one has a certain length in this position, but it is not a rod like a simple pendulum. Instead, it's a spring. Its length may change and is indeed changing. So as the object is falling down, it is not behaving as a rod of fixed length. It is just getting longer and longer and then shorter backward, and longer and longer, and then obtaining the initial length. Of course, during this motion, the length of the spring is necessarily increasing and passing by the equilibrium lowest position, not equilibrium, lowest position by the longest length, and then getting shorter and shorter, getting longer and longer, and then shorter as well. So the length is also changing. Therefore, there are two kinds of potential energy stored in the system. One in the gravitational potential, because the height of the ball is changing during these oscillations. On the other hand, some potential energy is stored in the spring by 1/2 kx squared. So there are two kinds of potential energy in this problem. Please be careful about it. We will just write as usual. The procedure tells us to write the kinetic and potential energies T and V. Write L as T minus V, and then take the derivatives and apply them, substitute them in this Lagrange's equation. So let's write the quantities. For instance, the kinetic energy T. The kinetic energy T, what is it? T is equal to 1/2 times mass times its velocity. But its velocity has two components. As the object is moving here, its velocity has two components. One along this radial direction, the other is along the tangential direction. Along the radial, let me draw the picture here, another picture. So this is the spring and object. This object has two velocity components. One along this one or that one, this way. It is called, written as x dot, because that variable is x. X is the amount of elongation or compression for this spring. But it also has a second kind of velocity, which is the tangential one. So it also has, maybe this way, tangential. That tangential one is just this angle is theta. So remember the equation from physics 101. So like V is equal to R times theta, for instance. R, what is R? R is this length. That length is generally B plus X, because B is the equilibrium length. So at any time, its length is B plus X. At any time, the length is b plus x, because b is the equilibrium length with no x. If some x is added to it, because the spring is elongated, stretched, then that additional part should be added, b plus x. So that b plus x is our radius now, and theta is the angle from the vertical. So that v tangential will be its radius b plus x multiplied by omega. So this is omega. Omega is, remember, omega is theta dot. So b plus x times theta dot, in other words, b is equal to r times omega in physics 101. So we use the term not omega, but theta dot, because theta is one of the two variables. There are two variables. One is the x, the length along the radius as it makes oscillations. The other is the angle theta that it makes with the vertical. So we will write two Lagrange equations for this problem. One for, in this case, one for dx, x, one for theta. So there will be x dot in the first, but theta dot in the second, x in the first, and theta in the second. So we will write two Lagrange equations and take two sets of derivatives, because there are two variables. Alright, so what is the velocity that we have to write here? M times, let's say, v squared, but what is v squared? V squared is just v radial squared plus v tangential squared. V radial squared is just simply x dot squared. The other is b plus x theta dot quantity squared. Because this part is just the tangential component of the velocity. Next, let me finally write this kinetic energy T. T is 1/2 m multiplied by x dot squared plus b plus x times theta dot quantity squared. Alright, this is the first part is the radial component, second part is the tangential component. Radius, this is like, remember, this is like radius times omega. So together it is a v component of v, and it has to be squared because there is the resultant. So the resultant velocity is this combination. What about the potential energy? Well, there are, as you see, two types of potential energies. One is positive, the other is negative. If you choose this level to be zero level for the fixed point of the spring, then vertically this object is at a distance of y is equal to minus that length times cos theta. So there are two parts. One is negative mg, and that vertical distance. That vertical distance is b plus x times cosine theta, because it is like this thing. So this part is b plus x, and that part is b plus x cos theta. But there is necessarily one more term for the potential energy. It is the energy stored in the mass spring system, and we know it is 1/2 kx squared. It is not b plus x, because b is independent of the elongation. B is the normal length. X is the amount of elongation or compression. So please be careful to write b plus x here for the total depth from the zero position, and x is the only component which represents the elongation or compression. So there are two terms for the velocity. One is positive, the other is negative. Now we will take the necessary derivatives. as we see here. First, let's consider del L by del X. First, let's write L, but let me write L first. It's a long expression, but let's write it. So L will be T M over 2 multiplied by X dot squared plus B plus X squared and theta dot squared. So let's write it as a square bracket. Minus V. So minus, but this term is now automatically positive, plus mg b plus x cosine theta, but this becomes negative, minus 1/2 k times x squared. So we will apply the derivatives to this final form of the Lagrangian. They are not difficult. We can easily get those simple derivatives. First of all, let's write del L by del X. This term. As you see in the first part, there is only one term here, x, so that it becomes twice m over 2 times this 2 comes in 2b plus x, and there is no derivative inside. And don't forget to write theta dot squared from the first term. Next, we continue mgx cos theta, so it is mg cos theta, mg cos theta, forget about b, mgx cos theta, and the derivative gives this one, minus 2's cancel kx, minus kx, and these 2's will cancel. So let's write it del n by del x as, after the cancellation of that, b plus x times theta dot squared plus mg cosine theta minus kx. Next we write del L by del X dot. This time let's apply the derivative with respect to the velocity. Del L by del X dot. But as you see here, there is only one term having an X dot, which is 2's, after the cancellation of 2's, it is mx dot. It is just m times x dot. There is no other x dot anywhere. And immediately let's apply the derivative, this one to the first derivative. d by dt del L by del X dot is simply m times x double dot. So we can obtain an expression here. So the first Lagrange equation will be, the first Lagrange equation is the following. First term d by dt del L by del X dot is just an x double dot. M times x double dot. Minus del L by del X, which is this whole thing, b plus x, theta dot squared, plus mg cos theta, minus kx, that's equal to 0. So this is one of the two equations, because we will also apply the same procedure to the theta and theta dot. We will apply the same procedure to theta and theta dot, the velocity, angular velocity, omega. Go back to L. L consists of these two steps, two lines. So del L by del theta now As you see, there is only one term having a theta. Theta dot is not theta. Theta dot is theta dot that we will use soon. But there is only one term having a theta dependence. It is this term. So mg times v plus x times minus sine theta. So it is negative mg v plus x sine theta. That's it. There's no other theta dependence. Theta dot now. Del L by del theta dot. Again, as you see, there is only one term having the theta dot dependence, which is this one. So m over 2 times the second part. But theta dot, this square cancels that too, so we only have an m. It is m times b plus x squared times theta dot. And there's no other contribution. Do we still need this L? No, we can manage. Now let's use the application, let's apply the time derivative on this expression. D by dt applied on del L by del theta dot. So it is d by dt applied on m b plus x squared times theta dot. Now in this case, there are two variables to be differentiated in this time, both x and theta dot. It is not just one term. So let's take m outside. M multiplied by derivative of the first with respect to t is twice b plus x. Derivative is x dot. Inside it becomes x dot times the other term plus b plus x squared, and theta now becomes theta double dot. So we obtain the necessary quantities. First term is this block, and the other one is already there. Plugging them in the Lagrange equation is what? First term, that is, we have m multiplied by twice b plus x dot theta dot plus b plus x squared theta double dot minus this single derivative, but it's already minus, so we write it as plus mg b plus x times sine theta. That's equal to 0, because this is the subtraction, and on the right we have a 0. Maybe we can have some cancellations. First of all, we can cancel the masses, if you like, or keep them. But anyway, we can cancel one of the b plus x terms. If you divide through by dividing through by b plus x, so this one, that one, and one of the other ones cancels. Therefore, we have m multiplied by 2x dot theta dot from the first, plus this remains b plus x times theta double dot, continue, plus mg sine theta is equal to 0. So this is our second equation. This is our second equation. So one of them represents the forces along the radial sense, the other the forces along the tangential way, torque. So these equations, for instance, it's a kind of exercise to get these derivatives, so it's a good exercise. So first equation, let me call equation 1 and the other equation 2. Equation 1 gives the forces in radial direction. Equation 2 gives the forces in tangential direction. Because we have here theta double dot, for instance. If you arrange it in a better way, theta double dot is angular acceleration. Theta dot is angular velocity, omega, etc. So these two equations, one is obtained by taking x as the variable, and so we obtained this equation by writing x dot and x. So it is related with the radial forces, irrespective of the tangential ones. And the second one is obtained by taking, instead of x theta dot and instead of x theta, we obtain the second one using the tangential forces. So at the end, this is in fact giving us the tangential forces. Now let's apply this idea to a third example, and then next time we will derive this important equation using some mathematical methods. Let's apply it to a new example where it is more difficult, as you will see, to solve by the previous methods. A block of mass m is held motionless on a wedge of mass capital M angle theta. All the surfaces are frictionless. When the block is released, block is the upper one, the other is called wedge. So when the block is released, is set free, when the block is released, what is the acceleration of the wedge? So this is a good problem to apply the Lagrangian equation. How to solve such a problem? Well, we first should set some reference frame. Let us choose a reference frame. Let me draw some 3 successive moments in this motion, because if you hold it, then it is at rest, yes. But if you leave it, as this block is sliding down the wedge is moving in the opposite sense, so they will be separating from each other. Still, there is contact between the blocks. Make sure that there is necessarily still some contact between them. However, to make it easier, we neglect all kinds of frictions. So let's draw 3 successive moments. For instance, this is the beginning, and the wedge is there, the block is there. Later, so this is the situation, sort of. As the block is sliding down on the wedge, remaining on the wedge, so as this object is moving in this direction and further, the wedge is moving to the left with some, of course, unknown velocity, unknown acceleration that we will find. So we should choose a reference frame. That reference frame, let it be x equals, choose an origin x equals 0, and let it be here. X equals 0 is the initial position of the block, let's say at the top. Later on, with respect to this origin, this one, the block, has moved a bit to the right. So this is the distance that's let me call x2, and bigger one has moved to leftward by some, has arrived at the position x1. Let's use 1 for the bigger one, 2 for the smaller one. This wedge has moved leftward because of conservation of momentum, as we will also make an interpretation. So this object, wedge is moving to the left. Let's call the position coordinate as x1. And of course it is moving to the right by x2. However, little one has also a y motion. It is going down vertically. So this is, let's say, x1, x2. And at a later time, let's continue this initial position. This is at the new x2. This is at the new x1. So the relative distance between them in the horizontal sense, the relative distance between them is x1 plus x2, because as for example one of them is moving leftward by 1 meter, if the other one is moving let's say 0.5 to the right, the distance, horizontal distance between them is 1 and 1.5, so 1.5 meter for instance. So we have to add them up. They are in opposite senses, x1 to the left, x2 to the right, but we should add them up to find the relative distance. On the other hand, little object, the block of little mass little m, is also moving down along the y-axis. So this one, for instance, this one, let's say here, this was the initial level it had, but here, for instance, this is the y, distance y covered vertically down. So when we write the velocities and potential and kinetic energies, we have to take into account the x's and y's. Alright. Now let us write the energies. Let us write the energies, kinetic and potential energies. Kinetic energy for the system, whole system. Whole system is just capital M plus little m. Capital M, the wedge is moving to the left with some velocity x1 dot. So that T consists of two terms. One half capital M x1 dot squared. But the other one is moving to the right. It has an energy 1/2 m x2 dot squared plus something else. What is that something? Y dot squared. But if you introduce a new unknown, because we can write only two equations, but if you have a third unknown y, for instance, we cannot solve for three unknowns with two independent equations. So we should find another way to express y in terms of given parameters. So consider this triangle. Which triangle? Let me show the triangle like this. For instance, this is the triangle. This is the triangle we should consider. Since this angle is theta, so is this. Therefore, in this right triangle, what are the components? For instance, what is tangent theta? Tangent theta is simply opposite side divided by adjacent. Y over x1 plus x2, because this whole thing is just x1 and x2, but the vertical one is y. So it is just y over x1 plus x2, and we want to find y. So y turns out to be x1 plus x2, x1 plus x2 multiplied by tangent theta, because tangent theta is always the same. Theta does not change during that motion. They are still in touch with each other. If they separate, of course, we will write it. So that y dot, then y dot is simply x1 dot plus x2 dot multiplied by tangent theta, and this squared will be substituted here. So that kinetic energy will be the following. T will be capital M over 2 x1 dot squared plus little m over 2 multiplied by x2 dot squared plus x1 dot plus x2 dot quantity squared tangent squared theta altogether. What about the potential energy of the system? Since the wedge is moving on its level, there is no vertical change and there is no spring in the system. So the potential energy is just the energy of the block, and it has fallen down somewhat, so that V will be, if you choose this level to be zero level, it is negative mgy. So potential energy is minus little mg times y. But what is y? Y is just, as we found here, x1 plus x2 tangent theta. So it is negative m times g times x1 plus x2 multiplied by tangent theta. So L is the Lagrangian, then the Lagrangian L is, it is just T m over 2 x1 dot squared plus the other m over 2 multiplied by x2 dot squared plus x1 dot plus x2 dot squared tangent squared theta minus this, but it is already minus, so it is plus mg x1 plus x2 multiplied by tangent theta. So this is our Lagrangian. Then we have to apply the derivatives to this expression. And we have two variables, one is x1, the other is x2. Theta here is not a variable, please note that. Angle theta is not changing. It is the angle of the wave which does not change. So we will never have such terms such as del L by del theta, del L by del theta dot. Theta does not change, unlike the previous example. So we only have two variables. We have two variables, x1 and x2. And therefore we apply the Lagrange equation to these. And x1 dot, x2 dot. So for x1, we should write it as, let me write the equation again, d by dt, del L by del x1 dot, choose the first one, minus del L by del x1 has to be 0. So let's take the derivatives patiently. Del L by del x1. Let's write the first one here. Del L by del x1. The derivative of the Lagrangian with respect to the variable x1. What is x1, by the way? Let me remind you that x1 is the horizontal component, position coordinate for the bigger object, the wedge to the left, and x2 is the horizontal component, horizontal coordinate of the little block at the top. So x1, look at the expression. Where do we see x1? There is no x1 here. x1 dot is something else. What is x1? There is only one term here, mg tangent theta. So it is just mg tangent theta. So we obtain this expression. Mg tangent theta will be this term. What about the first block? First we have to take the derivative of L with respect to x1 dot. There are two terms having x1 dot, this one and that one. So that, let me write it there. Del L by del x1 dot. Del L by del x1 dot. What is it? Start with the first, so we have 2's cancel and x1 dot. And capital M, x1 dot is the first term, 2's cancel, and we have this one. In the second group, we have only this term, so m over 2 multiplied by that, there's a square, don't forget it please. There's a square, so that plus these 2's will cancel, so we only have little m multiplied by x1 plus x2 dot. And then this tangent square theta. Tangent square theta. Okay? So x1 dot, this 2, that 2 will cancel m times this parenthesis together. But now we will apply this time derivative also to that expression. Let's apply this d by dt also to that final expression. d by dt applied on this one, and x1 dot plus the other terms. What do we get? First block will be m times x1 double dot. Single dot will be double dot, acceleration. Second term plus m multiplied by, these will be, both of them will be double dot, x1 double dot, x2 double dot, and tangent square is just there, it's a constant. Therefore, then what do we get? this block, which corresponds to the first block here, negative this term. So we have capital M x1 double dot plus little m x1 double dot plus x2 double dot multiplied by tangent squared theta minus this. But we can take it to the other side. Equals mg tangent theta. Equals mg tangent theta. Let's block it, box this equation and name it as equation 1. Using x1 and x1 dot, we obtain this expression. This is one of the two Lagrange equations. Now we should have something similar when we apply x2 dot and x2 here. Now, doing the same for x2 and x2 dot. Let's first get the x2 dependence. Del L by del x2. Del L by del x2. As you see, there is only one term having x2. There is no x2 here. This is only the only term. M times g times tangent theta, just like the first one. What about the other derivative? Del L by del x2 dot. There are two terms. Unlike the x1, there are now two terms for x2 dot. One is this one, the other is the second one. There is no such term here, so it will be little m over 2. Little m over 2 multiplied by, this becomes 2x2 dot. This becomes plus 2 again, 2x1 dot plus x2 dot multiplied by tangent square theta. And these two will, let's say, cancel for simplicity. Let's write it as little m multiplied by x2 dot plus x1 dot x2 dot tangent theta. So we obtained the necessary things. Now we should apply d by dt to the last expression, and then we will write a second equation. So d by dt, the applied on this last block is m times x2 dot plus x1 dot plus x2 dot tangent theta will be just single dots, will again be double dots. M times x2 double dot plus x1 double dot, x2 double dot, tangent theta. Again, let me repeat, since theta is not changing, we don't have anything like theta dot etc. So finally, what do we have? This block, d by dt, etc. This block, m x2 double dot plus this block, negative del L by del x2, which is this one. Let's take it to the other side. Mg tangent theta. So we obtain this one, like the first, it is called equation 2. Then our purpose is choosing to write them as something times x1 double dot, something as x2 double dot equals something, and x1 double dot again x2 double dot again is something else. By finding these coefficients, just like a simple two unknown problem, we can easily get x1 double dot and also x2 double dot. The two accelerations can be found relatively easily because it is not difficult to write them. Let's try to write them in this form finally and get the accelerations. From the first one, let's say x1 double dot multiplied by capital M. There's capital M plus this block little m tangent square theta. Little m tangent square theta times x1 double dot, yes, plus x2 double dot multiplied by m tangent square theta. M tangent square theta, second term, m tangent square equals mg tangent theta. Mg tangent theta. So this first one is obtained. What about the second line? For the second we will use this one. Now x1 double dot multiplied by, here we have little m tangent theta. Little m tangent theta, that's all, plus x2 double dot multiplied by little m plus little m tangent theta, equals mg tangent theta. So we can have some cancellations maybe. In the second one, we can cancel these m's. In every term there is an m, but not in the first one. Not in the first one. So we can finally obtain the accelerations. So let's write the first one. x1 double dot multiplied by sum of these two terms x2 double dot times m tangent square equals mg tangent theta. And the second one there is no m dependence. x1 double dot multiplied by tangent theta plus x2 double dot multiplied by 1 plus tangent theta equals g tangent theta. So by multiplying, setting these coefficients identically, we can get x1 double dot, x2 double dot. If you multiply this upper one by this one and lower one by the other one, for instance, x1 double dot multiplied by m plus m tangent square theta, but multiplied by this term 1 plus tangent theta, because we multiply the first one through by the coefficient of the second term, and x2 double dots will cancel. Of course, on the time we have mg tangent theta multiplied by 1 plus tangent theta. Multiplied by 1 plus tangent theta. What about the lower one? x1 double dot multiplied by tangent theta, but also it will be multiplied by the upper one, and tangent square theta, so that it will be g tangent theta multiplied by m tangent square theta. So that if you add them up, because x2 double dots have cancelled after the subtraction. This is negative, by the way. This is negative. This is also negative. We have subtractions because once we multiply the upper one by this coefficient and lower one by that coefficient and subtract the two, x2 block, x2 double dot block has disappeared. So we only have the subtraction of these two. Therefore, x1 double dot multiplied by m plus m tangent square theta minus m tangent cube theta is equal to, there's only another multiplication, sorry, x1 double dot multiplied by m plus m tangent square theta 1 plus tangent theta minus these m times tangent cube theta will be equal to the right hand side. What is the right hand side? mg are common terms. mg common.